The next component that we will look at in the Rankine power cycle is the turbine. So within steam turbines, depending upon the size of the power cycle that you're looking at, both impulse and reaction turbines are used. One of the characteristics of an impulse turbine is that it does more turning of the flow, whereas a reaction turbine will do less turning of the flow. It'll be similar to the turbine that we saw when we looked at the Brayton cycle. So what we're going to do now is we're going to take a look at a couple of different images collected for or of steam turbines. And this will give you a bit of an idea as to the magnitude and the size of these systems. So the first image shows a steam turbine. It's getting larger as you go towards the expansion. You can see very large bolts. We're dealing with very high pressures and temperatures. Quite often the lines will be insulated as shown in this image. And finally, in the last image, you can see the steam turbine open and the blades within the turbine itself. So that gives you a bit of an idea as to what the inside of a steam turbine would look like. Now, in terms of power output, the power output can vary quite significantly, as I mentioned earlier, depending upon the size of the turbine. And I apologize for the mixed units here, anywhere from a few horsepower, so a few kilowatts, to upwards of over 1,000 megawatts. Inlet conditions are going to depend upon the design of the particular Rankine power cycle that you're looking at. But typical 16 MPa, 540 degrees C, that would be in the range of values that you could expect for a standard steam turbine. There are supercritical Rankine power cycles that would obviously have higher temperatures and pressures, but this gives you an idea as to the ballpark range. Now, one thing about steam turbines that we do need to be careful about is we want to try to prevent moisture from forming as the steam is expanding. And moisture in the form of water droplets, so if we go into the two-phase region, can be very detrimental to the steam turbine in terms of performance as well as long-term reliability. So we try to avoid water droplets. So if we have water droplets, that is, if we're expanding into the two-phase region, so let me just quickly draw a TS diagram here. So we have our two-phase region, we're going through the pump, the boiler, we go into the superheated region. Now if we were to expand down into the two-phase region, that's what we're referring to here. So we want to try to avoid that, because when you go across the vapor line, you start moving into the two-phase region and you get water droplets, and those will impact the performance. And here we're saying that the efficiency of the turbine or a stage reduces by about 1% for each 1% of moisture present in the steam. So it's something that we want to avoid. Now there is a trick that we can play, and we will look at this type of power cycle in a future lecture here, but it's called reheating, where you only partially expand, oops, sorry about that. You only partially expand in your turbine, and then you would go back up in a reheat cycle, and then you would expand like this. And by doing that, you can actually avoid the water droplet forming. And that's called a reheat cycle that we will look at later on in a later lecture. So that's pretty much it for the turbine. The last component that we will look at in the cycle is that of the condenser, which we'll cover next.